Okay, I think we can start. Hello, everyone, and welcome to our next space seminar. Today, our guest is Armen Jaworski, CEO of CIM-labs, and his research interest is lunar dust and its interactions with spacecrafts and infrastructure. I hand over now to Dr. Jaworski, and he will give you a presentation. Prezentacji nie widać? Ale prezentacji nie widać? Czego?
Wszystko wydaje się dobrze.
Tak,
Jest
tak,
główny
tak.
ekran. Ja go współdzielę, więc...
Znaczy nie wiem, jak tam wygląda właśnie. Aha, okej.
Okay. Thank you for introduction and for invitation. It's a pleasure to be here at this faculty and to tell you about what we do in the topic of the lunar dust, but also not only lunar dust. So the title of my today talk is Simulations of Particulate Contaminations for Space Applications, including lunar dust. So at the beginning, I will also tell a bit more about other aspects related to particulate contamination. Okay, so just one slide about our company, who we are. So we solve engineering problems using simulations. So we develop new modeling techniques. We develop also engineering simulation software tools, and also provide simulation consultancy. Our scope of activities is broad. But in particular, the CIM-lab, which is part of CIM-mes company, we focus on space applications, and we do a lot of modeling related to contamination modeling for example, lunar dust under the T-rings. But we also simulate molecular flows, and we also simulate topics related to updated turbulence models, for example, for Mars entry. So in general, quite broad topics related to simulations modeling, numerical modeling for space applications. Okay, so going to the next slide, but for some reason, we can't go to the next slide. So maybe, yeah, now it works. Okay, so I would like to begin from just talking why this topic is important. Why contamination matters. So in general, it can lead to a mission failure. So in history, there were some cases that we know that one of the main reasons could be the contamination. But in general, you can think that, okay, if you contaminate some optics, it's obvious that you will have some scattering of light on top of it, that it will obscure the light, and it will be not as efficient as it could be. On the other hand, also in space, an important aspect is thermal balance, because you don't have a convective heat flux. So the heat transfers only due to radiation. So and you have a special radiation surfaces to emit the excess heat. And if you cover them with contamination, they will behave differently. You will have different absorption emission coefficients, and then they might not perform as they are designed. On the third reason why it is important is a mechanical wear. So the particles, the contaminants, the dust can impact the different mechanical parts, make them wear faster, or with the higher friction. Another aspect is electrical issues. The contaminants can cause the short circuit, leakage currents, so also make electronics not working properly. In general, all these aspects can lead to the system level impact. Particles are small, but the consequences can be large. For example, like in this example, one of the possible reasons of one of the failures of the Soyuz Progress 44 were due to contamination. When you think what is contamination, so this can be some small particles, but also, so it could be metal particles, it could be also particles coming from the skin flakes, but also other more elongated, for example, like fibers. Okay, so at the beginning, I will tell about our first research topic related for the particles. So it was the aim was to design, to develop a software which can simulate what is happening inside the rocket, inside the launcher during the launch phase, and how the movement of the shaking of the fairings. So the fairings are parts of the launcher which cover the payload. So how the shaking of these fairings can impact the detachment of particles attached to these fairings, and then how the change of the pressure and movement of air can transport these contaminants to some sensitive surfaces of the payload. And the main motivation was that some analysis research data show that this part of the development of the launching or developing the satellite and putting it into the orbit. So that these last parts, which are related to the encapsulation inside the fairings and the launch phase, they contribute very, very strongly overall. One of the main reasons why in which we develop the software tool. So what is happening during the launch phase, and what physics we should simulate? So at first there is a very fast pressure drop because the launcher is going up through the atmosphere. So in about 100 seconds you have change of pressure from atmospheric to vacuum. So this means that all the air, which is inside the launcher, has to go out through the vents. So here are some vents. Each launcher has vents in a different place, and they were different design. And this movement of air, which is going out, can transport or can act through the drag on the movement of the particles. Yeah. Second aspect, what is happening is acceleration. So you have acceleration coming from the engines, but then there are different stages. Sometimes engines are turned off, then there are separation of the stages. So the acceleration is changing. There is also a heat flux, which has quite important impact on the flow, because it is heating up the fairings. The heat flux comes from the friction of air, because the velocity of launcher is quite high. So there is a supersonic flow. There is a compression due to supersonic flow outside, and this causes the heat flux on the fairing, acting on the fairing. And then as it gets hotter, also the inside walls of the fairing are getting hotter. And this makes it that inside the fairings, you have a convection. So the fairings are heating up the air, and then the air has a lower density with respect to the other parts, and the buoyancy forces make them move. Okay, so when you look on the physics, this chart is supposed to represent it. So you have an airflow. In general, at the beginning, it's continuum phase. Of course, as you go farther, it goes to the transition and molecular regime. However, for contamination aspects related to particle contamination, we focus only on the continuum phase, because other phases, not much is happening in the transition and molecular regime. So the pressure inside the domain is changing. This generates the flow. Then the flow through the drag force impacts the movement of the particles, but the particles are also subject to the acceleration, Brownian motions, and electrostatics. And electrostatics can have a big impact, especially with relation of the force between particle and the walls. And okay, so the particles move, but then there is an interaction of particles with the walls. So at first, particles could be detached from the wall. But then also when they approach the wall, they can stick to it or bounce back. So there is also physics related to these interactions. And important aspects are the vibrations and shocks, because due to nature of the rocket engines, you have very strong vibrations, also shocks from time to time, related to liftoff or related to the separation of stages. And these two aspects, vibration and shocks, they can make particles to detach from the fairing. So they are very strongly impacting these contamination aspects. Okay, so to be able to simulate this physics, which I have talked about on a previous slide, we develop a software tool which is able to simulate it. So we can simulate pre-launch and launch case. So what it means? So when you prepare to the launch, you put the payload under the fairings of the spacecraft, and then you close the fairings. And the time between this closure of fairings and the launch phase is called pre-launch. And during this time, there is the payload is supplied with power, so it generates heat. So to take this excess heat out, you have air conditioning. And this air conditioning is moving the air. So also you have a risk of transporting the contamination. So we can simulate this pre-launch phase. And also then when you start the launch, when the launcher is lifting from the ground, then we can simulate this as a launch phase. So this tool was developed for these very complex phases, but you can also use it in other aspects related to cleanliness control. So you can simulate clean rooms, but also you can simulate, for example, airlocks on the moon. When you have let's say, an astronaut covered with dust, and then he wants to get into his habitat. So using the same tool, you can also simulate this problem. And we will show you some examples later on. Okay, so starting from the interaction between particles and surfaces. So I am smiling because the author of these models is sitting there. It's Łukasz Lech. So actually I could ask Łukasz, come and say what you have done here. Yeah, by coincidence, Łukasz is here. Okay, so in the end, you have different forces. You have van der Waals forces, electrostatic, capillary forces. And then we have different model to tackle, and to tackle two issues. One is a deposition or attachment. So it means particle is flying in the air and then wants to attach to the surface. And the second case is resuspension. So the particle is on the surface, but then at some point it may detach and start to flow. Yeah. So we have a separate models for deposition and resuspension. Yeah. So for deposition, there is a model called DLDO. So it can give you an answer if the particles are approaching the surface, whether it will stick or it will approach and bounce back. Yeah. So this is the model, takes into account different factors and gives you the answer, yes or no. It will stick or not. But then you can set up different conditions. You can also set up a condition that it will always stick. Yeah? So that the particle, when approaches the surface, always sticks. However, it can detach again, but then it's governed by the resuspension model. Yeah? And also the third option, escape, which means that it sticks, then it stays there forever. It will not resuspend again. Okay, when going to resuspension models, there are three main models implemented, but you can also implement your own model. So you can write your own subroutine, which gets the data which we have, and then based on this data gives you an answer. It will resuspend or not. And also we have a special model for the vibrations. So it gives you an answer how much vibrations can impact the resuspension. Okay, so yeah, vibration and shocks are very important because you have very strong vibrations during the launch phase. Here you have a kind of a spectra and the G, shocks. So the shocks could be up to 1000 G, so they're very strong. And from our experience, after making several analyses, we see that the shocks are really one of the most important factors which determine if the particles will detach from the fairing or not. Okay, the vibrations. So we, together with Łukasz Lech, we develop a special model which can take into account vibrations. So here we have some free curves. On this axis, there is a velocity, flow velocity. Then on this axis is a fraction remaining on the surface. And here you have curves for different vibrations levels. So this is without vibration. Yeah? So you see that the detachment starts from somewhere here. But then if you apply, let's say, 1000 meters per second square vibration, then the curve is going like this. Yeah? So for much lower velocities, you get the detachment. And this is the main idea of this model. Okay, so what we have done. So we developed these models. We took the literature data and checked how they agree with the literature data. And we got quite good agreement. This is the red line for the deposition models. For the resuspension, we also made our own wind tunnel, which is here. Quite small wind tunnel, but especially for this purpose. So we can make their airflow and monitor the number of particles which are left. And then we simulated this wind tunnel. So on the top left, you see the results of the simulation, and then compare the results. So this comparison of results you see here. Yeah. So it is also quite good agreement. However, after some calibrations, but we can say that these models are validated. Okay, so the first part was about how the modeling is developed. Now I will show you using this test case, how it can be used for the real case analysis. So we made a post-flight analysis of the Euclid spacecraft. So Euclid spacecraft is an observation satellite with very well, most relevant are the optics and the observation capabilities. So here you have a big baffle with opening, and inside you have mirrors and optics. There are very stringent requirements on the cleanness of these optical elements and also inner side of the baffle. So such scientific instruments, for such instruments, you always care a lot about contamination. So you make many analyses. And one of the possible solutions is to put a cover. So you put a cover on this baffle, which then could open in space. And of course, this gives you, it's lowering the risk that something will get to the mirrors. But of course, you tell the cover. And this cover is a critical element. If it will not work in space, then your spacecraft is useless. So it's always a matter of trade-off, if to put the cover or not. So in this case, they decided not to put the cover. However, they make a special adjustments of the fairing. So this is a Falcon 9 fairing. You see it here. Usually it is covered with the so-called FAB panels. So these are panels for damping the vibrations, damping the waves, the sound waves. But of course, they can have particles on them, and it's quite difficult to clean it because it's, let's say, a kind of a foam. So what they've done in this case for the Euclid, they decided not to have these panels and to have a special cleaning of the fairing. So the fairing was especially cleaned to reduce its contamination level. But anyway, cleaning is also not perfect, so some particles can be left there. So we made an analysis based on the real data, how many particles could, or what is the risk of contaminating the optics for these conditions. If you look on the payload, so here is the inner side inside the baffle. So you have a M1 mirror, which is at the bottom, M2 mirror, which is at the top. And actually, these were our main surfaces of interest. We made two types of models. Actually, we then made them simultaneously. First analysis was V1 and second was V2 in a, let's say, I would say half year distance. And the difference between them is that in first analysis, we neglected the internal cavities. So let's say there is no cavity below this mirror M1 in the first analysis. Yeah? And in the second, we took into account that there can be some cavity under the mirror M1. And this cavity is, it's reproducing the real cavity of the optical bay, the spacecraft. So what you see on the screen is a simulation of the particles suspended in the volume for some ISO 8 class, cleanless class, for different particle sizes from 1 micron to 18 microns. So I will play again this movie. So you can see that the heaviest particles, they tend to go down fastest. And if you go more into the smaller dimensions, then they more tend to go with the airflow than due to acceleration. So this observation is quite obvious because the big particles are much heavier compared to their drag, because the volume is to the power of third and the cross section is to the power of second of the radius. Yeah? But if you go to the smaller particles, they have bigger drag in relation to the acceleration forces. Yeah? So again, maybe, yeah, you see that the biggest ones, they just fall down according to the acceleration, and the smaller ones go and, yeah, here also they rotate a bit, and this rotation is caused by the flow and also by the heating of the pairing and the convection forces which are there. Okay, a small comparison of the two types of initializing the particles. On the left side are particles initialized from the fairing, and on the right-hand side from the volume. So in general, when you make such analysis, the big advantage is that these are quite small densities of particles. So you don't need to assume that they interact with each other, you know, that they collide. In this simulation, we neglect collisions. So the implication of this is that you can make many different analyses for different particle sizes separately. And then when you sum up the results, you get the correct results. So you can separately initialize particles on the surface, separately in the volume, use it divided by different beams, and in the end, you just sum up the number of particles on the surface. And using this, you can calculate the coverage of the particles of the surface, and this coverage is calculated, or we normally say that number of ppms. Yeah, so this is amount of the coverage of the surface by particles. Okay, so what is the result? The final result is the evolution of the contamination, because each surface has some initial contamination. Yeah, because when you have some contamination budgets during the manufacturing, you control the contamination levels, and in the end, you know what levels of contamination at each surface you can have before the launch phase. Yeah. So these values were set up, the initial ones, and then we simulated the launch phase and we saw the evolution of these contamination levels in time. So here you have different surfaces, different optical surfaces. So the blue curve is M1 mirror, the biggest one in the bottom, which you have seen on this picture before. And M2 is as a top. So you see that there is a rise of contamination of M1 mirror, which is logical. Yeah, it's facing upwards. You have particles going from top down. But then you have M2 mirror, which is this orange curve. So you see that the contamination decreased because the surface was facing downwards. There were some particles, probably the bigger ones detached, and the contamination reduced. Okay. Some analysis of the results for the V1 case without the cavity. inside the spacecraft. So you see that the airborne particles, so initialized in the volume, coming from the ISO 8 cleanliness class of the volume, that most of the particles are the smallest ones, which cover that surface. But actually, their let's say contribution to the contamination is 10 times less than from the fairing. Yeah? And this is the cleaned fairing after some special cleaning. And here, the main contribution of contamination is from the bigger particles. Also because the smaller ones tend to go to the vents. So yeah, and the bigger ones, they just more go with the acceleration. However, also the bigger particles have bigger cross sections, so less particles gives you much higher contribution to the contamination. Okay, so now I will move to the V2 case, which I call it. It's a case with the internal cavities inside the spacecraft, and I wanted now to focus a bit on the fluid dynamics. So you could see here that at 10 seconds, okay, there is no big flow from this inner cavity, but as we move forward with time, there is quite strong jet coming out from the inner volume outside. So this jet is caused by the pressurization. Yeah, so the pressure is going down under the fairings, and also the air which is inside this cavity wants to go out. Yeah, so it goes out through this main vent, which is the hole in the mirror one, and this is causing the movement of air upwards. And this movement of air is preventing particles from going there. Yeah, because then the flow is in a different direction than the movement of the particles. Also, what is interesting, the temperature under the fairings drops quite strongly. And also the reason of this is that you have a reduction of pressure. Yeah, so when you reduce the pressure, the temperature also goes down. Okay, so now just, okay, I will maybe put it like this to avoid having this on our screen. No, sorry. So comparing these two cases, first graph shows you the number of particles on the mirror M1. So when you include this flow from this vent, you get much less particles on the mirror M1. Yeah? And the main reason is that this flow is preventing them from going inside. The second observation with case, we reduced adhesion to also see what will happen when you have very low adhesion. So also in case of V1, you have some small particles when you reduce adhesion, but for the V2, you don't have them. And also one of the reasons is that you have this flow. Yeah, so the main conclusion is that, of course, the flow can have very strong impact on the contamination. And when you're simplifying your model, you have to always think about it, how it can impact the results. However, the good part is that you're on the safe side. Yeah, even if you don't include, if you would not include these internal cavities, in any case, you would get the contamination, which is much higher than it would be in the reality. Okay, so now I will finish the part related to the fairings, and I will move more to the lunar problem. So why we focus on the moon? Maybe a very general question. I think everyone who is observing what is happening now in the space world sees that the moon is a new goal, and there is a space race also with the recent change of the NASA goals. So not only ESA is planning to have the lunar landers. Saying not only because we are Europeans, so ESA is most interesting for us, but of course the change of NASA priorities, also the change of the SpaceX goals from Mars to Moon. So there are many companies focusing on this topic, and also, yeah, of course, the Chinese, but not only Chinese, also the India. They have their own goals for putting presence of humans on the moon. So when you talk about humans on the moon, of course, the last time they were doing the Apollo missions, from these Apollo missions, there was this famous sentence, but that dust is probably one of the greatest inhibitors to a nominal operation on the moon. So you see one of the Gene Cernan, commander of Apollo 17, and his spacesuits covered with dust and many things inside. Yeah. So, yes. Please.
It's just funny the image.
Sorry.
It's just funny the image.
Yeah. Okay. So. Why the dust is so different on the moon than on the surface on the Earth? Yeah, so of course the difference comes from the difference in the environments. Dust on the surface was made by the movement of air, of water, so the dust particles are they don't have sharp edges. Yeah, on the moon, the particles were developed by impacts of meteoroids. So and on the moon you have no atmosphere. So these particles are very sharp. They are also toxic. When inhalated, you have a very strong. You have many very small particles, and their adhesion is very high. They also are reactive, and also in the lunar surface, you have very strong impact of the solar radiation and the electrostatics. So you could have even up to several tens of volts of difference between illuminated part and the shadowed part. Yeah, so this generates very strong difference. And also here you see the distribution of the sizes with respect. Yeah, so number of particles with respect of the diameter. Okay, so key operations of the moon, which can impact the movement of the dust. So of course, landing and liftoff. So if you land on the surface or you want to come back to the orbit, you use the rocket engines. These rocket engines generate flow, and this flow can move the particles. So this is the first mechanism. Second is the rover operations. When you have rovers on the moon, they can also lift the dust, and this dust can cover these rovers and also make change its functioning. You have the airlocks and the internal flows inside the habitat, but you have also such interesting things like levitation of the dust. So due to radiation, due to charges generated during the lunar day and night, some small particles have the electrostatic potential and charges which make them levitate. So you have all these many different aspects which can generate the movement of the lunar dust. So the first topic which I want to focus is the landing on the moon. And now I want to show you the movie from the real landing of the Firefly. So you can observe how much dust is lifted. And also, okay, you see here a kind of rocks going out. Yeah. Yeah, a lot of dust lifted off. And this is very small lander. If you think about lander like a Starship, I think it's a really very high risk, not only for the Starship, but for everything which is on the moon. Okay, so, and now you see rendering of our simulation results. Let's say it's a bit similar view as for the Firefly, but to show you that we are trying to reproduce the re-landings. Yeah. So why we focus on this topic? Of course, at first to estimate the contamination on the lander and surroundings. So not only it's important how the lander will be contaminated, but for example, if you have some habitats or some other infrastructures in surroundings, you also want to know what is the risk of contaminating them. Because then eliminating this contamination is a big challenge. But also you want to estimate the risk of surface damage. For example, you have landing legs, so your thrust from the thrusters flow is lifting off the rocks, then these rocks can impact your landing legs and damage them. Yeah. Okay, so What physics, again, you need to take into account to make this simulation? So at first, the biggest challenge is a large number of particles at the order of 10 to 11, more or less for Apollo landings levels of thrust. So it's a very big number of particles. Yeah, if you would like to make a so-called Lagrangian simulation, so that each particle is a material point with 6 degrees of freedom, you would never be able to keep it in your memory of your computers. Yeah? So what we do, we divide these particles. The bigger ones we simulate in a Lagrangian way, but the smaller ones we simulate in the Eulerian way. What does it mean? Eulerian means that we don't simulate particles, each particle, but we simulate the density fields. So kind of a continuum field of the particles. Okay, large difference in gas density. So you have a vacuum, very high vacuum on the moon. So when you have a flow from the thrusters, in the beginning, the density is high, but then as you go much far from the lander, its density is getting lower, so you end up in the molecular regime. So we have different regimes of the flow. However, in most cases, we use just we use continuum to simulate the flow. But of course, you can. Not working. I can speak without microphone. It's also possible. I don't know, I just dotknąłem tutaj i nagle przestał działać, ale...
Dobra, tą może? Z góry? O, chyba działa.
Tak, działa. Okay, works. Great. Small break. All right. So, yeah, we usually simulate continuum also because it's much cheaper from the computational point of view. If you want to simulate DSMC in 3D, it's really thousands of CPUs, and it's very time consuming and of course resource consuming. Okay, impact of electrostatics. So in our model, we take into account electrostatics in our detachment attachment models. We also take into account the electrostatic forces and electrostatic potential modification due to the presence of the charged particles. We also take the initial charges from external tools. For example, Sp software. There is a software especially developed for the charging due to plasma. By ESA. Okay, strong interaction between particles. So this is a very important point. We take into account the collisions in Lagrangian approach, and these collisions have very big impact on the result. Okay, we have the custom deposition models. Okay, 0.6 and 7 are very complex, and we cover them partially. So we don't have a cratering, so-called. So we don't simulate the development of the crater. However, the user can define his own crater shapes at different snapshots of the landing, and by this way reproduce the shape of the landing site due to presence of the crater, and also the release of particles from the surface. We model using Robert's law, a bit modified to cover different particle sizes. However, it's important simplification. Okay. So just a slide about electrostatics. So we can take it as an input from the Sp software, and also we take into account the impact of how the electrostatic field locally is changing due to presence of charged particles. Here a slide about the Roberts law. So more or less you see the figure how it changes the released mass with respect of the radius. From the central point of the lander. It's case of Apollo. Here also on the picture on the right hand side you see one of the craters developed by the Apollo. So it is designed for Apollo landings, still commonly used, the Robert's law. It provides a rotative mass using the surface shear stress. Okay, so now example of the analysis. So we took the Argonaut lander, which is being developed by ESA and Europe. This is a public geometry which was taken from public sources about 2 years ago. Since that time, the design changed slightly. So it's more an example than the real results which we'll have on the real lander. But I think it shows well how you can use the software. So we simulated different levels, different heights during the landing. Also, we see a big impact of the thrust. So you see, for example, that this specific configuration of 5 engines of Argonaut makes that the thrust flow from the inner engine, because you have 1 engine in the middle and 4 engines around this single engine. So the green puff lines show the flow from the middle engine, and the red ones from the side engine. And the interaction between these flows in this particular case makes that there is a strong deflection of the puff lines from the middle engine upwards and hitting back the lander, which is of course very bad from the contamination point of view. Okay, we take into account collisions, and in this slide you see the difference. What happens if you take the collisions into account or you neglect them? Yeah? So on the right-hand side, you have a results with collisions, and on the left-hand side without. Small break. Okay, so you see that you have completely different result. And the conclusion is that in general, the movement of the flow due to vacuum is that it goes in every direction, more or less. So it's a bit different than you would have in a pressurized environment. But due to the collisions, you have a very strong diffusion of particles, and this diffusion makes that they go much higher than without collisions. Also, you have a very significant impact of the thrust. So on the right-hand side, you see 8 times higher thrust than on the left-hand side, and you see that the trajectories of the particles are completely different. Okay, so now I want to tell you a bit about this, maybe you can call it hybrid approach. So a Lagrangian Eulerian approach. So here you see a distribution of the particle sizes, and let's say what is the number of particles on the left on the vertical axis for different sizes. So let's say currently for us, kind of a border between a Lagrangian and Eulerian approach is about 200 micrometers. It's here. So imagine, so then we end up at about 1 million or 3 million of particles to be simulated. Yeah? Then if you move this curve to the left, for example, from 200 to 150 micrometers, you end up in 1 order of magnitude higher number of particles. Yeah? So instead of 5 million, you end up with 50 million of particles. So it's really, no, it's impossible to cover with Lagrangian approach the bigger part, the small particles, sorry. So that's why we developed this Eulerian approach. And we also validated this Eulerian approach. So we made the same simulation with the Lagrangian and Eulerian, and we get quite comparable results. So how, in the end, you make the simulation? What is the workflow? So at first, you need to know your destined profile, ascent or destined profile. So then you divide this profile into some snapshots. Let's say, I know, 50 meters above the surface, 20 meters, 10, 5, 2, 1. It's a decision by a let's say, engineer. Yeah? And then for each snapshot, you make a simulation, separately Lagrangian and Eulerian, and then you see when your rate of increase of contamination is getting constant. And then you take these rates for different levels, for different particle bins, particle size ranges, we call them bins, and just you put it into Excel sheet and sum up. And this is the approach. And you end up with such, for example, pictures, yeah, that you could see what is the contamination on the bottom side of the lander for different heights above the surface of the moon. For different particle sizes, this is the last column is for the Lagrangian, for the biggest ones, and then all these are for the Eulerian simulations. And then you sum up this, and you end up in the, let's say, number of ppms divided by particle sizes for different parts of the lander. Okay, so this was the part about the contamination analysis for the lander. Now I want to show you one more application of this analysis. So not from the perspective of the lander, but from the perspective of the infrastructure. So the NASA plans are to be, and also Chinese are to build very big, moon base, yeah, to many habitats, solar panels or nuclear power plants, whatever. All of these are quite sensitive to particles. Yeah, solar panels from the point of view of obscuring the sun. If nuclear power plant or whatever probably will have some thermal surfaces, which will be also very sensitive to particles. But you can also have particles which, they are heavy and they travel hundreds of meters per second. They can be like bullets, and so they can even they have kinetic energy, which could be harmful. So we made analysis how different shapes of the crater can impact the range of the particles, how far they can fly. Yeah? On this slide, you see different shapes of the craters, and let's say the map of the kinetic energy density and maximum kinetic energy for different range from the lander. So here on the scale we have kilometers, yeah? And I think this is quite optimistic, quite small range, but due to that this is made for small landers. If you consider heavier landers, bigger landers, I think the risk associated with the lifted lunar dust could be even on the orbit, because these particles could get velocity, which then make them to go in the orbit around and stay here, yeah? Lunar orbit. Okay, another application of this analysis is airlocks. So on this slide, you see an example of the flow of particles inside the airlock, yeah, from and with the astronaut covered by dust. Okay, last point, movement of the rovers. So on this slide, you see the movie of lunar roving vehicle made by NASA in the 70s. So you see that a quite substantial amount of dust is lifted. Also, this rover had problems with overheating batteries due to coverage with lunar dust. So for this reason, we also focus on simulations of the rover operations. However, these are quite preliminary activities. We have also a project focusing on simulating the interaction of lunar dust and textiles. For example, textiles for habitats, textiles for EV suits, and also for some shields. So we developed the simulation, and also we make some experiments to analyzing how to calibrate the simulations. Okay, so I came up to the conclusions. So in general, we develop simulation models for particle contamination and dust interactions. Using this modeling approach, you can estimate the contamination levels after ascent or descent. It is a software tool which can be used by engineers to find trade-offs and to reduce risk associated with the lunar dust. So yeah, thank you very much. This work was done with development team, also supported by sitting here Łukasz Lech. Also from ESA side, we have support from Bruno Bras, Mauricio Portaluppi, Ricardo Lampini, Małgorzata Hołyńska. Yeah, thank you very much.
Great, thank you very much for your talk. I think we have also time for some questions. Anyone from the, or maybe online? Not really. Oh, okay, yes.
First of all, congratulations for your company. I see that you have collaborated with NASA, and it's really impressive what you've done, guys. And my question is related to AI. I know it's impossible right now, but I need to ask. So these simulations somehow are possible to be enhanced using AI. Do you use it in your processes? How do you like integrate it with it? That's my question.
Yeah. Yes, now you can't do anything innovative without AI. Yeah, you know, we are focusing on physics-based simulations. Yeah, so always based on let's say physical basic laws, but of course you can always find the places where AI can support this. Yeah, we are now thinking and working on a topic to. Okay, I would call it reduced order models. You can call it AI as well, but something which kind of a tool which can support design of the lunar infrastructure by using reduced order models to account, you know, how different landings can let's say be a source of risks to this infrastructure. Yeah. So yeah, we are thinking continuing this. Yeah, or we can hear it because I think we hear the voice, but or if you can read it. Yeah. Maybe I can try to read it.
Hi, could I ask a question? Can you hear me?
Yes, please, we hear you.
Okay, perfect. So I actually have 3 questions, if that's not over the limit. So first I wanted to ask generally about the simulation model. Is more about like technical side, is more written in like C code, etc., or is more like, for example, approach with Python and PyTorch and taking advantage of GPU computing?
Yeah, it's written in C++ and Python. So the most computationally intensive parts are written in C++, and then the whole simulation chain is managed by Python. So we also use MPI for parallelizing the computations.
Okay, so now the second question, which is like my main domain, is do you use some physics-informed neural networks for solving some of the equations, or taking part of the simulation from like standards simulations into physics-informed neural network?
Yes, and what's the question? If we are using this?
Yes, I was asking if you're using, or you're planning to use, or
No,
if not, why not?
We are not using. Maybe we could, of course, but yeah, I'm not so much aware about. I know that there are considerations, yeah, to develop such approaches, but we are not considering yet to using this.
Okay, good. So if you ever think about considering, let me know. I can be happy to help on that. And then
Okay,
I have the last question, if I may. I was
Sure.
interesting because you showed these two regimes, one with the Lagrange and other with the Euler, and there was some border like 200 micrometers, if I remember correctly. I was wondering if you, I think you mentioned, but I wanted to make sure. So when you take these particles on the border and simulate with these two regimes, do you see like agreement between the statistics and everything? Do you like measure the, how to say that they agree in between these two regimes?
Yes, yes. One of the slides which I have shown has a comparison between Euler and Lagrange for the same, let's say, particle sizes, and we see the agreement between them. And also the Eulerian approach is it's not a simple advection. The equations are a bit more complex also to cover the collisions. However, most demanding is actually a detachment attachment for the Eulerian approach.
Okay, thank you. That's all the questions I have.
Yeah, thanks a lot.
Thank you. Very, very nice presentation and good quality of the images too. Thank you.
Thank you. Yes.
You've shown us how you manage input data, which you have shown us you have a wind tunnel, and for all the other data that you need. Do you also perform experiments to get the data, or do you get it from some research papers or ESA sources, or how do you manage?
Yeah.
Because I think you will need a lot of input data to perform with simulations.
Yes, you're right. It is not the biggest challenge, but one of the biggest ones to have a good data. So part of the data, of course, is taken from the wind tunnel, but it's more a kind of a calibration of the adhesion models, etc. But especially for the lunar problems, yeah, you just look into the papers and find something which you think is as close as possible. Yeah. So yeah.
Follow-up question: how do you validate your simulation?
Yeah. So the launch case, we validated all the models separately. We can assume that CFD is something which, okay, you don't need to validate very, very in detail. But of course, the particles, we can say that we validated this with the wind tunnel. Currently, we work on the project to make a validation for the full scale, which is not full, but let's say kind of simulating what is happening under the fairing in the scaled model. And for the lunar, we also now work on the project in which we plan to make experiments in the vacuum chamber. So in the dusty vacuum chamber, when you have a simulant of the regolith, you have some thruster or simulant the thruster, let's say nozzle with some gas flow, and then to measure the trajectories of the particles, simulate the same case in our tool, and then compare the results. Yeah. Of course, you can also try to simulate, the landings. The problem is that you have that one of the objectives of the many missions is to observe the trajectories of the lunar dust. So they put many cameras on the landers, but they don't share this data. So it's not easy to get.
Even though you are cooperating with.
Yeah, but okay, sometimes ESA is a big organization. It's not always the case that everyone has access to everything, and sometimes some data is data of the companies which are doing projects with ESA, so they have some confidentiality limitations. But I think if it would be European data, it would be easy, or much easier than data from US, for example. Of course, sometimes something ends up in the public papers, then you can try to use it, but it's not always the case, and not always you have all informations which are necessary to use this data. Yes, all the conditions associated to interpret them correctly. Yeah, please.
Question regarding the UP satellite. Did you cooperate with yourself? Did we get any feedback after the launch, or there was no?
Yeah. So this project was made with ESA. but it was a post-launch analysis. Yeah? So Euclid was already in space. We got the feedback that it more or less agrees with their expectations, what they think it was supposed to be. Yeah.
What kind of experiments will be useful to replicate, like in analog mission, or which kind of data will you find useful in that kind of analysis? And is there an impact of the exosphere, like the particles of red light that are on the surface versus the ones that are like floating in the exosphere?
I'm not sure if I understand your question. maybe starting from the first one.
Yeah. Like, is there any kind of experiment that you will find useful to like to do in an analog mission for this kind of
What do you mean by analog mission?
Like the ones that are made and Lunar is another lab research.
Mhm.
Like, is there any kind of applications that can be useful data for this kind of?
You know, I think any real data is always useful. Yeah, if it relates to the interaction of plume surface, any data is useful. In general, you know, the problem with the lunar surface is that you have very low information and very complex and very different physics from which we can reproduce on Earth. Yeah? So, for example, I told about the experiment which we plan to do in vacuum. Okay, great, we'll do it, but it will not reproduce electrostatics, for example. And because one, it's not easy to charge particles in a way that you know how they are charged. And second, we will never have such high vacuum as it is on the lunar surface, you know. So always real data, real experiments are a very important source of information, yeah? Especially for the moon. Because in general, it's really very scarce information currently.
Okay. And the second part was, for example, the red light particles that are on the surface of the moon, versus the ones that are in the exosphere, that is this time gap around the moon.
Okay. Yeah. Well, when we focus only on the landing process, you know, you could separate this. Yeah, I know that if the lander is going through these, let's say, clouds, yeah, I would make it a separate analysis of these two. And I think our model, well, you could use different models for this aspect. Yeah, but however, I think the landing of the heavy vehicles can increase the amount of particles on the orbits of the moon. And also, actually, I think you don't have a lot of data on the particles on this exosphere of the moon. You don't have many, or I don't know if exist observation, you know, satellites on the moon which observe dust. So let's say Earth orbits are observed quite accurately. But the lunar orbits, they are not so well observed.
But the question that I just come up that I don't even know, what is your business model like related to your materials?
Yeah.
How you get money? It's like startup, or it's like what is it about?
Yeah, thanks. Very good question. So, you know, well, our business model is like this. So, in general, these tools were their initial development, of course, was financed by ESA. And then ESA also uses these tools. But our approach is to develop a tool which then we can sell, or sell the consultancy together with these tools. So this is the main concept.
So you were part of the business integration center of ESA?
No, it's okay. Funding of ESA is very complex. But in general, you have something like the code's technology development program, or maybe different because it's TDE or TD. So these are low-tier projects from 1 to 3. And let's say you have some kind of a tenders, yeah, that ESA prepares a description, and everybody can apply to it. So we won a tender to develop the launcher simulation. And then this project was extended to also take into account the lunar dust. So these are just open tenders. Everyone can, write a proposal and try to win.
I don't know. Or you can build a company out of this kind of.
Well, I think it's you can use these tenders to develop to have financing for the development of let's say new products. Yeah, building company it's I think quite risky because you can win one tender, but then you can not win it again, and you have a big problem in your financing.
Any last question? About what kind of infrastructure or devices are you using for actually computing these models, because they are like quite complex. So I guess you need supercomputers. So
it's right. Like when I started, I finished studies about 2006. Yeah, so at that time the computers were a bit slower than now, and we were doing some simulations. Yeah, now the computers are much faster, and you do the same simulation, but you do it with a bigger mesh. And so usually you adjust your accuracy to your resources. So in this case, we have some strong computers in our company. They are not the strongest one, but we adjust what we can do to our resources. Of course, you have more resources, you can do it more accurately, faster. Here, like one CFD of this Argonaut computes about 2 to 4 weeks on close to 200 cores. Then one case of the particles, one beam takes about a week. Yeah. So yeah, it's a matter of if you want to have it faster, maybe if you want to have more particles. Okay, particles maybe not, because in Lagrangian you can't reduce the number of particles because you will have different results. Yeah, but then maybe a finer mesh or higher fidelity. Reproducing or maybe higher, bigger domain. So yeah, it's always a matter of trade.
Okay, thank you again for your talk. I think these technologies will be extremely important in coming years, given the interest in moon and its surface potential landings. So thank you again for your talk.
Thank you very much. It was a pleasure.